It's an example working out a problem with conservation of mechanical energy. We have a mass that's going to fall and make contact with a spring and then compress the spring. So this is going to be an application of mechanical energy conservation because gravitational potential energy coming from the conservative force of gravity, and then the elastic potential energy stored in the spring is coming from the elastic potential. So only conservative forces acting, and so we can use mechanical energy. Okay. When we're using conservation laws, we're going to think about things in being a definite pair or more of states. So in state 1, the mass is starting to fall. In state 2, imagine a situation where the block has compressed the spring and has just come to rest for an instant. Now, there's our compressed spring, and there's our mass at rest. Okay. We're going to measure the position such that this is where the gravitational potential energy is going to equal 0. It's when the spring is compressed by a distance x, because there's the equilibrium length of the spring. So conservation of mechanical energy is going to tell us is equal to some constant, and that is the initial kinetic plus potential and the final kinetic plus potential. And we're starting with, this is when the mass is first dropped. So it started at rest. And then for state 2, I pick that to be when the spring is compressed as much as it can be. Oops. So kinetic energy 2 is also 0. So we're working with, initially all of the potential energy is gravitational potential energy, and then we're going to have all energy stored in the spring, so elastic potential energy. So mgh plus x equals elastic potential energy stored in the spring, and the spring is going to be compressed by an amount x. So if this is where x equals, so there's x equals 0, from that distance down to this distance is x, and so the initial height of the mass is x plus h high. So all that gravitational potential energy becomes elastic potential energy. Rearrange the equation because we have a quadratic equation to solve. Move everything over to one side. I'll have a half kx squared minus mgx minus mgh equal 0. All right, and looking at those terms, there is our a, and the quadratic equation. A is going to be k over 2. There's B is going to be minus mg. And then C is all of that puppy. Minus mgh. So put that into our solution for the quadratic equation. Minus b plus or minus square root of b squared minus 4ac all over 2a. It's going to give us 2 roots. X is equal to mg plus minus bm squared g squared minus 4 ac is going to be minus mgh. We'll have a k over 2, and it's all under a radical, and we'll have 2k over 2. Alright, that simplifies a bit. X is equal to mg plus minus I have m squared g squared minus minus is a plus 4 over 2 is going to give me a 2 mgh times k. So both terms under the radical are positive, so I don't have to worry about any weird imaginariness. And there's a k. If you put in values, we got that to be roots of 10 centimeters and minus 8 centimeters. All right, so those 2 roots, where are those coming from? Well, I have 2 ways that I can solve this. The first one is to put this up high, right? H, which was given plus x, high, right? And then that would correspond to a certain amount of energy stored in the spring. The other solution is I'm a height h, but the initial displacement of the spring is going to be a smaller amount, just 8 centimeters in the opposite direction. So it doesn't fall as far, right? And results in less compression of the spring. So since we were asked in this question, what is the maximum compression, that is going to correspond to the bigger in absolute value of x for the spring, so 10 centimeters, 0.1.